So I believe we can get started. Hi, everyone. Thank you very much for joining another episode of Mari's Seminar. Welcome to our May seminar. We're super, super excited to be joined by a wonderful guest all the way from France, Lydia Nishimwe. She will be talking to us about making sentence embeddings robust to user-generated content. Such a wonderful topic, especially right now that we are trying to learn how generative AI models are working and so forth. So a little bit about Lydia. She is a third-year PhD candidate at the Indria and Sorbonne University in France under the supervision of Dr. Rachel and Sagard. Her thesis is centered around making NLP models robust to user-generated content, UGC, specifically posts from social media websites, for example, Twitter, Reddit, name them. She has published works on the lexical normalization of user-generated content and on user-generated content robust sentence embeddings. And she's currently exploring the robust machine translations of the user-generated content. So it's going to be wonderful. It's going to be great. I'm looking forward to it. Thank you very much, Lydia, for accepting to do a presentation at the Mari seminar. I'll just hand it over to you to share your screen and proceed with the presentation. I'll stop sharing.
Thank you so much, Millicent, and thank you all for having me. I'll just share my screen, and then we can start.
Yes, yes.
So let me know if it's working.
Yes,
Okay.
your screen is visible. Take it away.
Okay, thank you. So yeah, thank you all for having me. So I'm really excited to present this work. It's actually work that I presented last week at the LREC Calling conference. And it was this paper was co-authored with my supervisors, Benoit Sago and Rachel Borden. And I'm happy to present it to you today. So I'm going to start with an introduction to just kind of set the background or the context in which we work, because I wasn't sure who would be in the audience. So I thought maybe it would be nice to make sure everyone is on the same page. So for some of you, some of this background information might be familiar, but bear with me. And then after that, I'll share the motivation behind this work and why we're doing this work. So the context is NLP, natural language processing, which consists of taking input text, and processing it using a model to get, let's say, output text. So this is one example of the architecture or the structure you would have for an NLP model, where you would have, for example, in the case of translation, you would take your input sentence, let's say an English sentence, you would pass it through an encoder model, which is usually a neural network. And that encoder model will give you a vector representation of the input sentence. And then from there, you pass that to a decoder model, which will generate your output sentence. So in the case of translation, as I said, the output sentence would be the translated sentence. So if you're doing English to French translation, for example, your input would be an English sentence, and your output would be a French sentence. So we also have many types of NLP tasks. We have tasks that usually have like this encoder-decoder structure or architecture, such as machine translation, text summarization, and so on, where you need your input text passed through an encoder and then a decoder and then your output text. But we also have encoder-only tasks. So these are tasks where you only need your encoder to represent your input text into some sort of vector representation that has that captures the meaning of the input, and then you do some other task like named entity recognition. So that would be if you have an input sentence and you try to recognize which are the names of places or which are the names of people and so on. Then you have decoder only tasks, which don't have an encoder. So it's only the second half of this architecture. So these are tasks that generate text. So the common example would be GPT, which is known for the text generation or text completion tasks. So in our case, today we're going to focus more on the encoder only type of NLP. And as I said, we take an input text and then you pass it through a neural network and it does some computation and then you get your output. So what we need to bear in mind is that neural networks or encoder models and so on, they only understand numbers, while what we're working with is natural language, is text. So we need to find a way to represent text as numbers. And the way we do that is through word embeddings. So here I have, I found this is not mine, so give credit to Hariom Gautam, but this is a nice simplified representation of what word embeddings are. So you have here, I'll just turn on my pointer. So you have words, let's say this is your language and these are all the words in your vocabulary. So this is an imaginary language with only 4 words. But so for each word of your vocabulary, you want to represent it as a vector, so as a series of numbers. And what we have here is that you take, for each number, you take some sort of feature that describes your word. So here we have an example of 7 features. So this would be a 7-dimensional vector. And then what we find is that words that have similar meanings or words that are related to each other have numerical values that are close to each other. So this means that the vectors that are represented by this series of numbers are close to each other in the space. Now I talk about space, but this is a 7-dimensional space, which we cannot easily represent or imagine even. So what we usually do is you do a 2D representation of the space. So you just project your 7 dimensions to 2 dimensions and you have something that looks like this. And here you can see that the words that are related are close to each other and the words that are not are a bit further from each other. So this is a space that has learned that has some sort of semantic properties. We also find that some relations are also represented in this space. So for example, man is to woman, what king is to queen is also represented in the space. Now, this here is what, so this matrix here, so where we have 7 features times 8 vocabulary words, this is what we would call your word embedding, your embedding matrix. And usually how you get these numbers is that you train your model on data. So you can randomly initialize all these numbers and you train your model, and the more your model sees textual data, the more it learns to map the words that are similar, close to each other, and so on. So these numbers, they get better and better with training. I think that's all I can say for word embeddings. And now we're going to talk about something very important. It's tokenization. So as I said, we're working with text and we need to get to numbers. We need to get to word embeddings or vectors. So when you have a sentence like this, the first thing you do is you split it into units. So the units are what we call tokens. So the first level of splitting that you can do is word level splitting. So word level tokenization. So here, each word is a token. And so when you do this, you get word embeddings like we have just seen. But the problem with this approach is that, as we saw, you needed a matrix that had your whole vocabulary size. So this means that for your language, you would need to account for every single word in the language, which would be enormously a large number and also not practical in terms of computation. But also, it means that when you encounter words that you don't know or words that are misspelled, then they're out of vocabulary. So what we usually do is we split the sentence into subwords. So how this works is that words that are very frequent tend to be kept as is, but words that are more that are less frequent tend to be split into more frequent subunits. So this is what we have here, like sentence was split into two. And this is very useful because it helps you reduce your vocabulary size, so you don't have to account for every word in the language. But also, it's very good at handling words that it has never seen. So if it sees a new word or a misspelled word, it just breaks it into smaller and smaller units until it gets to the smallest unit, which is the character, and which is also the third level of tokenization, the character level tokenization, where each character of your sentence is the unit you're working with. So why are these units important? Because we need them to get to the embeddings. So I showed you word embeddings before. Here we have an example of subword embeddings. So you're working with, let's say, one word, apple, that has been split into two subwords. So you're going to have one embedding vector for the first token and another embedding vector for the second token. And so instead of one word embedding, you have two token embeddings. In the case of characters, one example is the embeddings used by character BERT, where you go from your word, you split it into characters, then you have character embeddings, so you have one vector for each character, and then you go through a convolutional neural network to kind of just compress all that into one single vector, and you get your one vector for your word. Now, one thing I didn't mention before is that the example I showed you had a dimension of 7 features, but in real life, the models we use would have hundreds or even thousands of features. So the dimension would be very, very, very huge. But then the model just learns the values, but also learns the features. So we don't know explicitly what each dimension represents, but we trust that through learning, the model has produced something meaningful. So I've shown you what word embeddings are. Basically, they are a way to represent words in a space that has some semantic properties, that where words with similar meanings are close to each other, or words that are related are close to each other. So now what we're working with are sentence embeddings. So sentence embeddings are the level that's the higher level. So you have vectors to represent your sentences such that sentences that have similar meanings will be close to each other. So how do you achieve that? Well, you go from your input text that has been tokenized. In this case, you have 6 tokens. You pass that into your encoder model. So let's say BERT, for example, and then some computation will take place, some transformations will take place. And for each of the input tokens, you will get an output token or word embedding, which will be a contextualized word embedding. So this means that the values you have here represent the word in the context of this sentence. So for example, in this sentence, how do I learn Python? The representation for Python will be different from when you have a sentence where Python actually means the snake, where in this case, it means the programming language. So it will depend on the context. And then once you have your contextualized word embeddings, you go through a pooling layer. So you pool them together. That means you merge them together to get one fixed size embedding. So there are many strategies for merging. You could do the average of all tokens, of all embeddings, and then you get one embedding vector. You could also do the maximum value of like across each dimension, then you get one, or you could pick one of these to represent the whole sentence. So the idea is at the end, you have only one fixed embedding vector to represent your sentence, whereas before you had as many tokens as you had in the input. So why is this important? It's because it has so many applications that are very useful. So some of them include semantic textual similarity. So the idea is that since you have a way to represent a whole sentence in a single vector, you can compare the similarity between two sentences by comparing the similarity between two vectors, or the distance between two vectors. And this is useful because it allows for tasks such as plagiarism detection or just paraphrase identification and things like that. It's also useful in a multilingual setting. So if you have the same sentence in two different languages, the vectors would be close to each other because they mean the same thing. So this is very useful for the task of bytext mining, which is used to collect sentence pairs, translated sentence pairs from the internet that are then used to train translation models. So it's very useful. Another use case would be maybe your search engines or your question answering, where you would represent or encode your question into one vector, and then all the possible answers or all the possible documents into other vectors, and the vectors that are closest will be the most relevant answers. So it has many applications. The sentence embedding model that we'll be focusing on in this work is LASER. So LASER is it's a large-scale multilingual sentence embedding model that was trained like for 93 languages, and it's widely used, especially for bytext mining. So initially, it was just an encoder, a multilingual sentence encoder, but then they realized that even though it had its support for 93 languages, the low resource languages were not represented so well compared to the higher resource languages. So they trained other encoders specifically for those low resource languages, but they made sure to map them onto the same space as the main LASER, the regional LASER encoder. And then after that, other work was done to extend it to the speech modality. So where instead of encoding sentences written in the text form, you would encode your sentences in the speech form, so using speech units. So that way in your space, you have vectors that correspond to text and to speech that mean the same thing, being close to each other. And then after that, they trained decoders on top of this whole space, where you can have speech decoders and text decoders. So LASER is now a whole ecosystem of sentence level models where you can do text-to-text translation, text-to-speech translation. You can do speech-to-text translation and speech-to-speech translation, even in language pairs that you have not seen during training, or in modality pairs that you have not seen during training. So that's one of the main reasons why we decided to work with it. So I'm just going to give you an example of what I mean when I say sentences that mean the same thing are close to each other. And I'm going to use a cosine distance. So it's a distance metric between two vectors. So here I have the sentence "see you tomorrow" on the left, and I have its translations in French, German, Spanish, and Kiswahili. And then I have a paraphrase like "let's meet up tomorrow." And on the right, I plot the distance between LASER's embedding vector for the first sentence and the second sentence. So as you can see, for the first three text pairs, so the French, English, the French, German, and Spanish translation, the distance between those vectors and the English vector is very small. It's less than 0.1. So which means the vectors are very similar. They're very close to each other in the space. Here we have the example of Swahili, where the distance is much, much bigger. So you have 0.6 of distance. So this is what I was saying when I said that low resource languages are not represented as well by the original LASER model. And then lastly, we have a paraphrase, which is not as close as the other translations, but it's also not very far. So this is this is what I would say one of the things that differentiates LASER from other popular sentence embedding models is that its main focus is on trained for translation pairs. So it's very good at finding translation pairs, not as good as at finding paraphrases compared to the other models. But it's okay. We'll continue with that. So the second focus of our work is what we call user-generated content. It's also commonly referred to as internet language or something similar. So the idea is that when people write, especially on the internet or on social media platforms or in text messages as well, you have a lot of lexical variation. You have a lot of phenomena that are, I would say, creative. Sometimes you also have mistakes, but sometimes they're not even mistakes, they're intentional choices. So this writing style is very, very particular because it varies or it differs from the standard way of writing, especially in this case you have English. You also have some new words or some slang words that come. So it's like almost a variant of English. So what we find is that when you try to embed these sentences with LaSER, so we're still using the same sentence here tomorrow, but now we write it in a more creative, user-generated type way. And then we compute the cosine distance. We see that the distances are very, very big. Like LaSER is not able to recognize that when this sentence here tomorrow is written like this or like this, it should be exactly the same thing as the standard sentence. So this, you can imagine that this would be a problem, especially for the tasks where we were expecting sentences that have similar meanings to be close to each other in the space. So those tasks, you would have a poor performance, because in this, when you try to use this kind of text, this kind of user-generated non-standard text, because LaSER is not able to put them at the same place as the standard text. And this is not just specific to LaSER, it's actually common to many natural language processing tasks where you have a performance drop or a drop in performance quality and inequality when you try to work with user-generated text. So just to play around, I tried to translate this sentence here tomorrow into French using the Microsoft Bing translator to see how well it would do. And so this is the standard sentence here tomorrow translated as I don't know, so that's perfect. And then when you start adding this lexical variation, the model is lost. Like sometimes it translates maybe half of the sentence or one word, and then the rest it just copies it because it has no idea what to do. Or sometimes it almost works. So this is a case where it was like the space was misplaced, and the model actually recognized it and even asked me if I meant to write it like this. And it gave a good translation. Not a perfect translation, because "abientôt" means see you soon and not see you tomorrow, but it's still acceptable. So you can see that the negative effects of text that is written this way are across the board, like on all tasks, not just sentence embeddings. So just to kind of recap what we're working with here. So we have a multilingual sentence embedding space, which is the LaSER space. We have a LaSER encoder model, which is a multilingual sentence level model that produces single embedding vectors for each sentence. And this space has the properties that sentences that have similar meaning will be close to each other in the space. And because LaSER is multilingual, this works for translations, such as "à demain" and "see you tomorrow," but also for paraphrases in theory. And then what we find is that when you write this standard sentence in a non-standard way, LaSER is not able to put it in the same neighborhood in that space as the standard sentence. It does not recognize it as the same sentence. So what we want to do is to have an encoder that will be able to put the standard English sentences in the same place as or close to LaSER standard English sentence embeddings, but also we want to put the non-standard sentences in that vicinity as well. So this is what we will call a robust English sentence encoder. It's robust to user-generated content. So that is our goal. That was our motivation as well. So now I'm going to explain to you the approach that we'll follow to try to achieve that. So here we're going to train a model, this model using a teacher-student approach. So this means that you have your teacher model, which is LaSER, and then you train a model that you want it to mimic or to imitate your teacher model. So when you pass a standard sentence into your student model, you also pass the same sentence to the teacher model. And then you train your model to minimize the distance between its sentence embeddings and LaSER's and the teacher's sentence embeddings. So you're really copying, you're mapping yourself to the same space, to the same place in the space. And then now the difference comes in is when you pass a non-standard sentence to your student model, you pass the standard equivalent to the teacher. So now the student learns to map the non-standard sentence close to the standard sentence in the space. So this is the teacher-student approach that we're going to use. And our teacher model, as we said, is LaSER, the original LaSER, which will be fixed during training. So it does not change, it does not get trained or fine-tuned or anything like that. And then we're going to compare, we're going to train two types of student models. One of them is going to have a subword input embeddings. The other one is going to have character level input embeddings. So the reason why we want to try character level is because the literature has shown that character level models are usually more robust to noise in the input text. So we're going to see if that works well also in the case of sentence embeddings. Not going to go much into the technical details of the architectures and all that, unless there'll be some questions at the end. I could come back to this. But the idea or the main focus, the main thing to remember is that we're teaching our student model to imitate only the standard embeddings of the teacher model, whether it sees standard or non-standard sentences. And then now, one of the challenges we have when you're training is that you need to have your standard and non-standard sentence pairs, which we don't have in general. We have a lot of non-standard text on the internet, but we don't have many aligned standard and non-standard sentence pairs. So what we do to generate, we generate our training data artificially using this data augmentation tool called NL Augmenter. So it has the implementations of many types of transformations that inject non-standard phenomena into sentences to make them look like realistic user-generated content. So we try to select a few that match to what we tend to see on the internet. And then, so how we generate the data. So we have 12 transformations here from NL Augmenter. We randomly select a subset of those transformations using a probability of 0.1. And then we shuffle them. And then finally, we randomly select the values of parameters for the transformations that require parameters. So for example, this thing transformation corresponds to butterfingers, so that's keyboard typos. And when you apply this transformation, you need to give it the probability of inserting a keyboard typo in your sentence. So the default probability is 0.0.5. And what we do is we select this probability randomly by, we select it randomly between half of this value and half more than this value, with a probability of a quarter, a half, and a quarter. So we do this for all the transformations that require parameters. And then in the end, we have our transformations and the parameters that we're going to apply to our sentence. And we call this the mix all transformation. So here in this sentence, for example, it has applied abbreviations. Well, there are two types of abbreviations, but it has applied abbreviations like for nothing and people and to get and so on. And it has included a keyboard typo at tried, which became tried with a W. So the reason why we do it this way with all this random and shuffling and all that is because we want to ensure that the model will not always see the same transformations together, that the same transformations are not always applied in the same order during training. So we want to make it as random or as uniform as possible. And so what we found in what we get in our training data is that with this method, you have at most like 37% of sentences have at least one transformation that has been applied. 28% have zero transformation, so the student model still sees the standard data, and then 23% has two transformations, and so on. And in terms of the transformations, we find a uniform distribution. So the model has seen all types of transformations during training. So now I'm going to describe a little bit the experiments and the experimental setup that we're working with. So first, I'll start with the evaluation data. So as I said, we don't have a lot of parallel, standard, non-standard, aligned data. So the few that we have, we're going to use them for evaluation. So this is an example of from multi-lex norm is one data set with sentences with almost 2,000 sentences from Twitter, which are like non-standard and then normalized or standardized versions. We have RoxMT, which also has almost 2,000 sentences from Reddit, which have also been normalized. So we have the alignment here, and it has also been translated into 5 other languages. And then finally, we use the Flores 200. So Flores 200 only has standard text, but in 200 languages from the Wikinews, Wikibooks, and Wikivoyage domains. But we're going to use it, and when we use it, we're going to augment it artificially with one of the transformations that we saw. And then, so the training data that we use is we get monolingual English data from the Oscar dataset, and then we augment them with the mixed all transformation that I previously explained. So so this gives us some sort of bilingual, standard, non-standard training data set. And then we're going to validate on the Flores dev set, which we augment with the mixed all transformation. And for training, as I said, we have 2 student models that we're going to compare. So one will be the token level input, and the other one with the character level input. So the token level input has the same architecture as Roberta, and we're going to initialize the model weights with Roberta. And the character level model has the same weight, has the same architecture as character BERT, and we're going to initialize that with character BERT. And then we call our 2 students RoLASER for robust laser and CRoLASER for character RoLASER. So now I'm going to describe the evaluation metrics that we use. So the first one, I kind of alluded to it before when I showed you the demo. It's the average pairwise cosine distance. So this computes the cosine distance between each sentence pair, and then computes the average over all the sentences in your data set. The second one is called XSIM, and it stands for cross-lingual similarity search. So this is a metric that is used for bytext mining. And the way it works is that if you given text, let's say bytext in 2 languages. So let's say you have English, French aligned translations, pairs or sentence pairs. You encode all of them to get sentence embeddings for each sentence, and for each source sentence. So for each source embedding, for each English embedding, you're going to compute the French embedding that is the closest to the English embedding, and then you're going to verify if that embedding is the translation of, if that sentence is the translation of your source sentence, then that is a good alignment. If it is not the translation, then that is an alignment error. So what we're going to compute with XSIM is the alignment error rate of aligning your sentence pairs. And then there is also XSIM++, which is a more challenging version of XSIM. So what they did is just to augment your the target sentences, so for the English sentences. So for example, if you have a sentence like, I this bag costs $200, they're going to duplicate that sentence maybe like 3 times or 10 times, and then instead of $200, they'll put $500 or $50 and so on. So you have sentences that change the meaning, but have like minimal surface changes. So this makes it more difficult for your model to select the closest one. So that's why it's a more challenging metric than XIM. But what we need to remember from all these metrics is that the first one, average pairwise cosine distance, tells us how closely the models embed non-standard sentences to the standard counterparts. And the last two tell us how well the models align non-standard sentences to the standard counterparts. And then, so now the things we're going to consider are what we're going to evaluate, or what we're looking for, the questions we're trying to answer. The first one, does robustness to artificial user-generated content translate to robustness to natural user-generated content? Because I remind you that we're training on artificial data, so we want to see if it will also work well on natural user-generated content that was written by real people. And then we're going to try and see if the student models can replace LaSER at representing English sentences in a multilingual setting. So if you want to align English with French, for example, can you just take out LaSER and put our model for the English, and will it still work the same? And then we want to see if the robustness to UGC will degrade the performance on standard data, because that's also something. You want to make sure your model is more robust to user-generated content, but you want to make sure that it does not, that the performance on standard data does not suffer. And then the last one, we want to see if the robustness that we see in the sentence embeddings will impact the performance on downstream tasks, which I'll describe later. So we're going to go into the results and the analysis portion. So the first one was wanted to see how this works on, whether our student models work on natural user-generated content. So here I have the 2 data sets we had, so multi-lex norm, which had Twitter data, and RoxMT, which has Reddit data. And at the top, so we have we're comparing the average pairwise cosine distance. At the bottom, we have XIM. So here you want a lower, if you want a lower value, because you're trying to minimize the distance and to minimize the alignment error. So we find that our models are better than LaSER at both with both of these metrics, especially for so RoLASER is better here on RoxMT. And here we have the character level model, which is better, has a better cosine distance for multi-lex norm, and not a similar XIM to LaSERs on multi-lex norm. So then what we want to see now is if we can do a visualization of what's actually happening in the space. So here we pick a random sentence from RoxMT, and then we plot the embeddings, the embedding vectors. So in the center, we're going to start with the LaSER's standard embedding vector. So LaSER's embedding of the standard sentence. And then we have the LaSER's embedding of the non-standard sentence. We have the LaSER's embeddings of the translations into the 5 languages. We also have the embeddings of our student model, so RoLASER and CRoLASER. So what we find is that with LaSER, as we said before, the distance between the standard and non-standard embeddings is very big. It's even bigger than most of the other languages. But with our model, our first student model, RoLASER, the distance between standard and non-standard is smaller, much smaller than LaSER's, and both the standard and non-standard embeddings are close to the center, so they're close to LaSER standard embeddings, which is what we're trying to achieve. However, we find that for the character level model, the distance between standard and non-standard has reduced. So this distance is much smaller than this, but we're still far from the center. So we're still far from the standard embedding from LASER. So this means that the character level model has managed to reduce the distance between standard and non-standard embeddings, but it has failed to map the standard embeddings, its standard embeddings to LASER standard embeddings. So it has only solved half the problem. Yeah. And then now we're going to see how each of these transformations affect the models. So we're going to work with artificial UGC and we're going to evaluate on Flores. So Flores has only standard data, and we're going to augment the Flores, the English sentences of Flores with first with the mix all transformation, then each sentence only with this abbreviation transformation, and then only with the other one, and so on for all 12 transformations. And then we're going to compute the XIM++, so this is the alignment error rate between aligning the standard sentence and the artificially augmented non-standard sentence. And then we're going to try and see also which ones are the most challenging for LASER, and how do our models fare in this context. So we find that the lead speak, so lead speak is this kind of transformation where you replace letters with characters or digits or something like that. So lead speak is the one that is the most challenging for LASER, because this is where LASER had the highest error rate, the highest XIM++. And when you try to understand why, we realize that when you do this kind of transformation, you apply character level perturbations to your text. And these character level perturbations break up your subword tokenization. So here, where hello world was divided into 3 tokens, now it has 2, 3, 4, 5, 7 tokens. Or 8, it has 8 tokens. So the injection of this kind of perturbation has shattered your subword tokenization. So that, and we find that the other transformations that are the most challenging for LASER, such as butterfingers or keyboard typos, and space, which is the random insertion or deletion of white space, they also do this this shattering of subword tokenization, and that's why LASER performs the worst for them as well. And then we find that across the board, our model RoLASER has significantly reduced this alignment error, especially for lead speak, but also for all the other transformations. And RoLASER, the character level model, has not managed to improve the performance of LASER, except maybe for the 3 that were the most challenging for LASER, but for everything else, it actually degrades the performance of LASER, and that this is to be expected because, as we showed before, the character level model has not been able to map itself properly to the standard embedding, to map its standard embeddings to LASERs. And now I'm just going to show you an example of LASER when I evaluate LASER on all the 200 languages of the Flores dataset. And I plot the alignment error rate compared to English. So that's the XIM++. And as you can see, we start at 0 and then we get to 100. So an alignment error rate of 100 means it fails completely. So here we have some low resource languages for which the LASER representations are not very good, but we also have languages that LASER does not support. And then, so what we see is that when you try to put the alignment between standard English and UGC English into this plot, you find that some phenomena like lead speak, as we said, are also very high in this list. So they're very challenging. They're more challenging than all these other languages. And then you have some more that are challenging. So user-generated content is so challenging that LASER fails to recognize that it's still English and aligns other languages better than user-generated content. Then we evaluate the in a multilingual setting, we want to see what happens when we use our student models to encode English, and then we use LASER to encode the 5 other languages, and we try to compute the alignment because we're still in the same LASER space. And in the source sentence, so the English sentence will be either standard or non-standard. So when we start with the non-standard sentences, we find that when our model RoLASER has a better alignment score between, let's say, non-standard English and Czech, it has a better alignment than LASER itself. And we find this across the board for all the 5 language pairs. However, the character level model it still performs the worst, which is to be expected. And when we're working with standard English, so we encode standard English, we find that our model is comparable to LASERs. So it has not degraded the performance of LASERs on standard data. And we find this across the board on all 5 language pairs. We do the same evaluation in the other direction. So this time we align Czech to English and French to English and so on. We find similar patterns. So when the English is non-standard, RoLASER model is better than LASER, and this is the same for all the language pairs. And when the English is standard, our model is comparable, sometimes slightly worse, but mostly comparable to LASERs. So it does not degrade the performance on standard text, which is what we're hoping for. And finally, we also evaluate on downstream tasks. So the downstream tasks I'm talking about here are sentence classification. So where we take our embeddings and we train a classifier on top of that to detect the sentiment labels in your sentence. So is it a positive sentence, a negative sentence, or a neutral sentence? So we use this task, the tweet sentiment extraction classification task. We also take 2 sentence pair classification tasks where now we're predicting whether 2 sentences are paraphrases. So we also use 2 Twitter sentence pair classification tasks. And the last one is the semantic textual similarity task, which examines the degree of semantic equivalence between 2 sentences. And we use the STS benchmark for this. So the first 3 tasks are on Twitter data, and the last one is on more standard data. And we find that our models, in this case, we're looking at accuracy and the like. So we actually want to have a higher accuracy. So we find that our model performs better than LASER on the first 3 tasks, which are on non-standard data from Twitter. And on the last task, it is comparable or it matches LASER's performance. So this is also what we were trying to see. And then here, the character level model degrades the performance of LASER, which is also expected by now. So I'm going to wrap up first by bringing us back to the example that we started with. So this is still the demo where we had the standard sentence, see you tomorrow, and the non-standard sentences written in creative ways. And we compute the cosine distance for the 3 models. So as we said, LASER was very bad. So here we see that both our character and RoLASER models have reduced this distance as well. So to sum it all up, we set out to make a LASER English encoder that is more robust to user-generated content. And we achieved this by using a teacher-student approach to minimize the standard UGC distance in the embedding space, and by generating training on synthetic user-generated like data. Our RoLASER model, student model, was significantly more robust than LASER on natural and artificial UGC, while matching or improving LASER's performance on standard data and downstream tasks. And we also found that RoLASER did not perform well because it struggles to map its standard embeddings to LASERs. And we found that the most challenging UGC phenomena are the transformations that shatter subword tokenization. And in the future, we plan to extend RoLASER to more languages and to their corresponding UGC phenomena. So I thank you all for watching, and welcome any questions you have, and I invite you to check our paper and the demo app and the code and the models on GitHub. And thank you so much.
Amazing. Thank you very, very much, Lydia. I enjoyed your presentation, like from slide one to the last, and I hope like everybody has truly, truly enjoyed. I mean, this was wonderful because it has given us a clear picture of how what exactly is going on in generative AI models, right? Being NLP models. We have so many questions. I wonder if you'd want to not they are very interesting questions actually. I wonder if you want to read them or should I read them for you? And I tried to
Yeah,
answer just one, which I was very, very sure of. I
okay,
note
yeah,
that
you
BAT
can
is
go
always
ahead.
an
Go ahead.
encoder. BAT is an encoder model, and GPT is a decoder based model. So, the first thing Clement was asking, how do you select features to use for word embeddings? That was you in your initial the first slides, right? I, I think you can just answer that and then I read for you another one.
Yeah, maybe I can try to go back to the slide, but the answer is we don't. At least we don't anymore. So
Yes.
that I think I don't want to go into too much detail because I might actually make something up that's not true because way back when in the early days of NLP, they
Mm,
used to do feature engineering, but what they found is that data-driven approaches are actually better because you just by looking at the data, your model kind of learns which features are important to understand or to represent the language. So that's why I said nowadays it's very hard to know what those features actually represent because it's just very abstract, but it's meaningful for the model because it has. So I don't want to venture into trying to explain how feature engineering works because I've never actually done it because I think that is before my time. So I just want
yeah,
to get back
I,
to the.
I get it.
I mean,
Should we actually
maybe
move
some
to?
people still do it though. Like maybe it's still done, but definitely not in
Yeah,
neural approaches. I think like I guess some people still do some feature engineering in other tasks, but definitely not in my task. So I don't want to say something that's not accurate.
yeah. I think let me just read for you the next. If the embeddings are generated based on context, does that mean that we don't store a static collection of embeddings for each token? If that's the case, what is it that uh, is learned if not the actual embeddings? How do you represent or encode the fact the fact the fact the embeddings can change based on context, the context.
Yeah. So the answer is the the first, like the input layer, like for example here, so let's say this is your BART input. This word piece embedding, this will be your static uh, your static embeddings. So even though like after training and so on, this is what will be static. So which means like the embedding for app will always be the same. The embedding for poll will always be the same. But then, so that will be here at the input layer. Oh, let me turn on my pointer. So that will be at your input layer down here. But then the contextualized word embeddings are what you'll get as the output of your encoder. So down here is still like the context hasn't been taken into consideration yet. So that's the input. It's the static lookup table that you pass as input that you use for the input is static. But then at the end, the output will be the contextualized word embeddings. And
Mm-hmm.
then how the model learns how to encode the context. Well, that's the model weights basically. So here you have
Yeah.
your model, like it's a bunch of functions like linear functions and computations and so on that have parameters. Those are your model parameters or your model weights, and those parameters get updated during training. And by the
Mm-hmm.
time you finish your training, you have a set of parameters that will allow you to have the same like contextual localized embeddings, like when you have a certain input. So it's this, I guess the model parameters are what store like the how to get from the static to the contextualized.
Makes a lot of sense. Now, if you are passing standard and non-standard sentence pairs, I'm curious to know how much of such data you have and how you ensure that it generalizes over real-world scenarios that were not in your training data.
Yeah, so that's a good question, and it's an open question because so yeah, in terms of data, so like I said, the actual standard and non-standard pairs we have are in the thousands, so maybe 5,000 sentence pairs or something like that. So it's not a lot because you generally need millions to train your model. So the challenge of when you're training with artificial data is you're trying to match the distribution of the real data. So that's always a challenge. And so here what we did was, maybe I can try oops, oh, sorry. So here, what we did was try to look for phenomena that are more, that we see online, I guess. So we try to be as close as possible to that. Yeah. So we try to pick some things that we generally see, like misspelling, contractions, slang, and so on. Some of these, for example, the misspellings, some of them are based on rules, like keyboard typos are based on your QWERTY keyboard and like what's the probability of selecting, of typing a W instead of an E. That's a QWERTY keyboard, like that's just a rule-based thing. Some of them are based on dictionaries, like slang dictionaries, things like that. Common misspellings, I think, were from the Wikipedia, like the Wikipedia edits. You can get common misspellings from that. But these are all, as you said, kind of static because new words keep coming up, and they don't cover every possible creative way of writing. So what you are hoping for, what we're hoping for here is that because we're not trying to learn the exact spelling, but we're trying to teach our model to, like when you see something that looks funny, just map it to the standard thing. So we're trying to teach it to kind of erase that distance or that noise implicitly. So we are hoping that that's what will make it generalize better to unseen and like exact unseen patterns. But yeah, so and one of the things we can do here to improve the performance, like I said, we only used a probability of 0.1. So this is like 10% of noise in our training data. We can also try to increase the percentage of noise in our training data to increase robustness, to see how that would work. We can also try a more sophisticated methods of generating data. But yeah, but that's definitely always a problem when you're working with artificial data, is that you're never quite going to map the distribution of the real data.
Thanks so much for that. So this one is from David, and I think Clement, Marcy, and myself, we are both interested in it. So the question is, I wonder how this would transform text that is a slang, which may use some standard phrases from known languages while combining it with others as well.
So can you give an example? Do you mean something like code switching? Like, let me see.
Codes, so there is code switching, but
Something
also
like,
there is just a slang. I mean, here in Kenya, we also have slang. I wonder if you've heard of something called sheng. Have you ever heard of
yes,
sheng?
yes, yes, yes.
Yeah, so sheng is a slang.
Okay, yeah.
English, Swahili-based cant here in Kenya in its slang. So that's yeah.
So basically, the example I can think of is like when you say matri instead of matatu. Is that what you're
Those
saying?
ones now is the sata. Yes.
Okay, yeah. So this is something. Uh, well, let's start with code switching. Code switching is like a whole different field on its own, because it's so complex as well. So code switching is when you mix, let's say, two languages, which we also definitely do a lot of in Kenya, between English and Swahili. So, and then there's slang words where you're creating a new word in one language with the rules of the other language, something like that. So right now, my model, I don't think can do that because I trained it only on English. But my next project is to train bilingual, robust bilingual model. So I'm going to see if we have some of that crossover, like, because one thing we found, so I explained the laser ecosystem when you can have a decoder. So I tried to play around with it, and sometimes when you take, like, I try to play around with the when you take an English sentence and a French sentence that mean the same thing, and then you combine the vectors, and then you kind of get something like in between, you know. So I'm sure that, like, they do this model, this space does have some code switching capabilities, but it's something that needs to be like really studied, and it would be really fun to see what it can do. Yeah, I'm also curious.
Yeah. Yeah, and that's a huge space to, extend this exciting work. Lydia, once again, thank you very, very much. This was a wonderful presentation, wonderful insights. Congratulations for your acceptance of your paper and, presenting it at, you said ALREC, right?
Elrek calling, yeah.
Yes, Alrek, yeah. And to our participants on the call, feel free to grab Lydia's paper. I shared a link on the chat, and I'm also going to share this, the presentation. She will share it with me, and then I'll paste it on the chat as well. Thank you very much for joining. Gimau, Jackie said this is a wonderful presentation, and everybody, I think, we loved your presentation, honestly. Thank you very much for coming. Yeah.
Thank you so
Uh,
much for having me.
right. We will invite you again. Please
Oh, thank you.
extend this work, one, to African languages, and two, to now these
To
slang sort
share.
of like languages. Yeah, it will
Yeah.
be really great. It's a wonderful research. Many thanks, Lydia. Have
Thank
a
you.
good day, and everybody, thanks again for joining us, and I'll keep you posted on our next seminar. Bye.
Okay. Thank you. Bye bye.
Bye.